So organic chemistry is huge. If you're going to do anything in medicine or biology, you've got to know about organic chemistry. If you're going to do anything in chemistry, you've got to know about organic chemistry. If you're going to be an engineer or a materials scientist, if you're going to make plastic, you've got to know about organic chemistry. So today what we're doing is starting with an introduction to naming and understanding the structures of organic compounds. We're talking about organic chemistry. Now, organic chemistry, as you saw from the video earlier, involves a naming system, a nomenclature system that includes prefixes that tell you how many carbons there are in a chain. And so when we're naming non-organic covalent compounds, we said we didn't, except for carbon monoxide, we didn't use the prefix that stood for one carbon. But we do have, I guess it's really more the root word for the carbon chain for one carbon, and that's that's meth. Okay, so meth is a prefix for one carbon in a chain. Okay, meth is a prefix or root word that means one carbon in a chain. All right, one carbon in a chain. Eth is the prefix that means two carbons in a chain. Prop is a prefix that means three carbons in a chain. Okay, I'm sure you're familiar with the term propane. Okay, that's three carbons in a chain. Bute, and it is pronounced bute, okay, is four carbons in a chain. All right? So pent, now this starts to sound a lot like the prefixes we used in non-organic. Pent is five carbons in a chain. Hex, six carbons in a chain. Hept, seven carbons in a chain. Oct, eight carbons in a chain, like 8 tentacles on an octopus, okay? 9, non, and 10, dec, and we'll leave it at that, okay? We won't try to name carbon chains longer than 10. Okay, now there are, well, as you saw from the video, names for all kinds of carbon chains, all right? Longer chains than that. Now, so what does that mean? Well, let's go back to Lewis dots, okay? Our electron dot structures and things like that. If I have one carbon, and I don't guess you can call it a chain here, one carbon, the carbon has 8 valence electrons, and it has to bond with 4 things to have a full valence level. Well, the terminator, you all know what the Terminator is, right? The movies, right? Yes? No? Really? Oh, yeah, Arnold Schwarzenegger? Oh, man. Okay. All right. You don't like movies. Okay. Anyway, the terminator for the chain is the lowly hydrogen. Okay? Lowly. You know, it's a tiny one, small one. Okay? So we're going to put hydrogens all the way around this in order to fill up all the electron slots we need for the carbon. We get a Lewis dot structure that looks like this, and then a Lewis formula that looks like this. And we're pretty much going to go straight to Lewis formulas. We're not going to keep drawing all of this all the way through this, okay? But this is the formula for methane. Okay, it's a Lewis formula for methane, and we're going to start giving this a little bit different name. In organic chemistry, we call that a structural formula. Okay, it is a Lewis formula, but it's also one of the structural formulas, and we'll call this a complete structural formula. Okay, we'll call this a complete structural formula. Okay? Now, as you saw from the video, these organic compounds can get huge. If we tried to name, like for instance, a protein, by the IUPAC names, it would fill up a book. All right, so we need some shorthand, and this is where we start using kind of not only sort of a verbal shorthand, but also a formula shorthand. And we're going to use what's called a condensed structural formula that looks, in this case only, just like the molecular formula for methane. CH4 is the condensed structural formula. For methane. It also, in this case only, happens to be the molecular formula. Okay, it is also the molecular formula. All right? So you see where we're going with this so far? And we're going to introduce you to another structural formula, but I've got to build a larger molecule here to get to that. So, that's methane, and that's about all we need to know for the moment about methane. Let's do ethane. Can you think you can draw a complete structural formula for ethane, just based on what I just said? Do it. Draw a complete structural formula for ethane. Well, 2 carbons. That's where you start. Then you put as many hydrogens on there as is needed to fill up the valence level of the carbon. Boom. You got ethane.
Isn't there like a formula you can use for how many like carbon to
hydrogens?
Yeah, carbon.
Yeah, I probably won't be teaching you that in here. If the subscript on the carbon is N, then the subscript on the hydrogen is going to be 2N plus 2. Okay? But you don't need to know that in here. All right? I'm more interested that you understand the structures themselves and try to come up with some kind of a formula for writing these. All right? Then that's for what are called alkanes, and we're dealing with alkanes right now. We'll get back to that in a minute, what it means. Okay. All right. So we got 2 carbons. We're going to bond the 2 carbons together. I need 3 more hydrogens on each carbon. Now you're overthinking it, right? Okay. That's not so hard, is it? Okay. So this is a complete structural formula for ethane. Now the condensed structural formula is going to look a little different. In this case, condensed structural formula now at this point becomes the individual chain links, if you will, okay? The carbon-hydrogen groupings. So we write a condensed structural formula in this form. Okay? That's a condensed structural formula. Okay? So complete structural formula, condensed structural formula. Does that make sense? CH3, CH3, that's what we got there. And an organic chemist, or really any chemist, would look at that and know that's what the structure is, just by looking at the condensed structural formula, because they know there's only single bonds to the hydrogens. Boom. Got it?
Could you write it CH3 in parentheses?
You don't do that, but there is a time for that, which we will not learn in this class. Okay, when we get to really long chains like this, sometimes you can see it written as the middle parts in parentheses with a subscript. But we won't be doing that in this class. Okay? All right, now, so that's ethane. Propane. Why not? You can do propane, can't you? All right, do propane. So this is a complete structural formula. This is a condensed structural formula. And propane has 1, 2, 3 carbons. Enough hydrogens to fill the valence level. Okay, does your complete structural formula look like mine? Okay. And the condensed structural formula, CH3. Notice the center carbon here only has 2 hydrogens on it. So that's CH3, CH2, CH3. And there's a condensed structural formula. Okay? Now you can imagine if we get really, really long chains, even this is going to get pretty cumbersome, right? So we have something called a skeletal formula. And if you ever open up the drug packet that comes with it, even sometimes even over-the-counter drugs now have them in there. They show a line formula for whatever the chemical is. That's built on this idea of a skeletal formula. Okay. So in a skeletal formula, listen carefully now. In a skeletal formula, you're only drawing the bonds between carbons. You have to infer. Actually, the structure itself implies, and you infer, the location and number of the hydrogens. Okay? So the bonds between the carbons, I just got 2 bonds, right? So a skeletal structural formula looks like this.
How do they expect people to know that?
Because with organic chemistry, the structure is built on carbon. So if there's nothing else there but those, the end of the line is a carbon, the corners are carbon, and the line's a carbon.
But I'm saying like the people who buy the drugs.
Oh, well, they might not know that. But it would be really overkill to try and draw out all the carbons and hydrogens and stuff. People aren't going to understand about double bonds and resonance structures anyway. So, yeah.
So, the little thing that you just drew, so a carbon would be on each side.
You could say that. Okay. The end of a line or at a corner, there's a carbon there. And you know how many bonds a carbon has to have. So if this carbon has 2 bonds coming off of it, it's going to need 2 more, so there's 2 hydrogens there. You can infer that from just that drawing. Does that make sense? All right? So now we got 3 different types of formulas in this organic system, okay? Why don't you do butane then? Butane.
Organic chemistry is built off of
a carbon chain. Organic chemistry is built off of a carbon chain. Okay? So, in fact, one definition of organic chemistry is the study of chemicals where you have at least 2 carbons bonded together. Of course, the exception is methane. That's considered an organic chemical, even though it only has 1 carbon. Okay? 2 carbons, at least 2 carbons bonded together. That's one definition. I'm not sure that really fits everything. There are some non-organic structures that have 2 carbons bonded together that really you wouldn't consider to be organic. So it's a little more complex than that, but generally speaking, that's a pretty good definition. If you've got at least 2 carbons bonded together, you can assume it to be an organic chemical. Okay? All right, butane has, what are we doing, 4 carbons, right? 1, 2, 3, 4. Enough hydrogens to flesh it out. And we got a complete structural formula. Condensed structural formula. Skeletal structural formula. Carbon, 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 carbon. And then you have to infer the number of hydrogens needed to completely flesh it out. So if this carbon here has 2 bonds on it, one going to the right, one going to the left, or sort of up to the right and up to the left. This has 2 bonds on it. I need 2 more. I know I need 2 more hydrogens there. So I can infer there are 2 more hydrogens there. This carbon's on the end. It only has 1 bond showing, so I know I need 3 hydrogens there. So this is representing the same thing as this.
okay. So for ethane, you wouldn't just put or does the skeletal structure start at?
Well, yeah, we could write ethane's skeletal structure formula to be a line and be kind of, you probably wouldn't know if I did it, all right, what it meant, right? So I kind of skip over ethane, even though technically, yes, ethane can be a single line, all right? That makes sense? Yes.
If it were any more, does it just continue to zigzag? Is that what it does?
Well, you could actually draw it in any shape you want to. We could also do butane like that.
So it doesn't matter.
Doesn't really matter.
Okay.
Okay?
I was supposed
Sure, you should know that's an ethane because you got 1, 2, 3, 4 carbons.
That's butane.
I'm sorry, I said ethane. I'm sorry, I was talking about ethane. This is butane. You're right. Butane. Okay, got that? All right.
Okay, so you count how many carbons there are, and then, but how do you infer how many hydrogens there?
If it's on the end of the line, it's got to have 3 hydrogens.
Okay.
If it's in here, it's got to have 2 hydrogens. So far. Hint, hint.
Until there's a double bond.
Until there's a double bond or a triple bond or some other functional group. True. You hate the functional groups? How do you know? We haven't dealt with functional groups yet. Okay. Okay, well, good. You can help other people. And you're sitting right in the middle of class? That's perfect. Okay. And now, but that brings me to this point. Let me make this point really clear. We are going to, in this class, we're not going to follow IUPAC rules 100%. There are a few deviations from IUPAC rules, okay? Now, any organic chemist seeing the names that you write in here, or the formulas will be the same. But if you're writing a name, sometimes the names will deviate slightly from what's really expected. But any organic chemist will know what you mean by the way we do it in here. But what I'm doing is trying to eliminate some of the exceptions you're supposed to do and keep it simple, okay? KISS. Keep it simple, silly. Okay? Got it? All right. Okay. Now, so let me introduce you to how double bonds work then. So this suffix A and E actually has a meaning. So the prefix part, or really the root word here, means 4 carbons. The ane means all single bonds. So these carbon chains we've been talking about so far fall into a class called an alkane. This is the class of chemical we've been naming so far, where there's nothing but single bonds. Okay? Nothing but single bonds. Those are alkanes. When we get to structures that contain a double bond, then we have something called alkenes. Okay? So these are all single bonds throughout. And then when we get to alkenes, we have at least one double bond in the structure. Okay? Between carbons. Alkenes means there's a double bond between carbons. What?
What is the suffix for that? Like if
E and E. Yep. Okay? So all of these chains that have nothing but single bonds are going to have a suffix of A and E. But once we introduce a double bond, then we're going to call it something ene. Let's use butene here as our example. Okay? I'm going to put a, well, let's see. I tell you what, let's go back. Let's actually go back to ethane here. Let's go back to ethane and make it into a double bond. All right, so it won't be ethane anymore. It's going to be ethene. So we've only got 2 carbons in the eth. Okay, but that ene means I got a double bond. So there has to be a double bond between the 2 carbons. Does that make sense? So there are 4 electrons shared in here. So up to now we haven't really used the Lewis formula a lot. We've been using Lewis dots a whole lot. I introduced you and told you how to write Lewis formulas. Now we're really going to use Lewis formulas a lot. We're going to call those structural formulas in organic chemistry. And so if I've got 2 bonds going to this carbon, how many more hydrogens do I need? 2 more. Put 2 hydrogens on there. 2 hydrogens on this one. And I've got an ethene complete structural formula. Okay? Now, once you introduce a double bond, you've got to show the double bond in the condensed structural formula. So as long as there are nothing but single bonds, okay, we don't have to draw any double bonds in between these carbons. But when we get to a double bonded structure, we have to show the double bond between the carbons like this. Only, well, I shouldn't put it that way. It's be CH2 double bonded CH2. And that will be a condensed structural formula for ethene.
So you show the double bonds in the formula?
You show the double bond in the formula. And I think where they came up with this was when you used it on the old typewriters, when you didn't have all the computer stuff, you could put an equal sign in there and show a double bond. Okay? I don't know that. That just reminds me of that. Of course, Most of you guys have never typed on an old typewriter, an old manual typewriter. Have you? Pretty interesting. Okay? They had one down front as a kind of a display for the 50th anniversary of the school year for a while. That was really interesting. I used to work on those. All right. So then when we get to propane, or propene, we're going to have 3 carbons, okay? And so the double bond can only go between one or the other. It can't go between both of them. All right, don't worry about why for right now. So I'm going to put a double bond over here. Okay? And so I need 3 hydrogens on this carbon. I need 1 on this one, and then 2 on this one to finish it out. Okay? Now, remember we talked about how hard it is for students to think in 3 dimensions when you're in high school? Okay? I want you to, in your mind, spin this 180 degrees. Can you do that? Can you spin it in your mind 180 degrees? And so you get this if you spin it 180 degrees. So I think. Okay? Did I change the chemical? No, I just spun it around 180 degrees, right? So you got to know that this means the same thing as that. Okay? Yes?
Why is there 1 hydrogen on the one in the middle?
Yeah, you got 2 bonds here on the carbon, 1 here, so you just need 1 more hydrogen. Okay? All right. So this is propene. Okay? Propene.
So
What's the condensed structural formula? Well, I'm going to have a CH2. I'll do this one over here. Doesn't really matter which one of these 2 you do. At least in this class it doesn't matter. And then this one's going to have 2 or CH and then a double bond and then CH2. There's a condensed structural formula. Okay? How about a skeletal structural formula? For what? No, there's only 3 carbons. 1, 2, 3. There's a double bond between 2 of the carbons. There it is. Okay? All right. So that's propene. I'm going to do a butane here, but this is where we're going to have to start changing the name a little bit more. Okay, you have to start changing the name a little bit more with butane. All right, now let me put down 4 carbons. 1, 2, 3, 4. If I have a double bond and I put the double bond here, if I have a double bond here between these 2 carbons and I flipped it over, it'd be the same as putting the double bond here, right? If I put the double bond here, that's a different chemical altogether. So now we need a way of designating where the double bond is. Okay? And so we use a numbering system. Let's put the double bond over here to start with. Okay? So this is, I got 2 hydrogens here, 1 hydrogen here, 2 on this hydrogen, 3 on the last one.
Why is it one hydrogen on that one?
Because this carbon has a double bond, that's 2 bonds on this side, a single bond on this side. Those bonds take up 3 bonds. I just need 1 more to finish its valence level. Okay? So, we have to have a system for telling everybody who's reading the word where that double bond is located. Okay? Now, this is where we're going to deviate a little bit from IUPAC rules, because when we get to more complex stuff, it'll follow that pattern. We're going to call this but 1 ene. Because it tells us it's on the first carbon. It starts on the first carbon. So it goes from the first to the second carbon. That's considered to be on the first carbon. Okay? So if I flip this upside down or flip it 180 degrees, the double bond would appear over there, but that doesn't change the name. At this point, then, we're going to start numbering the carbons to give us the lowest numbers to the most important functional group. Okay? In this case, this is the only functional group we have. So that's going to be a number 1. Okay? Let me repeat that. In order to number where this numbering system tells us where these functional groups are located. In order to find the functional group, you're going to number from the end of the chain to that functional, that's the most important functional group, in whatever end of the chain gives you the lowest numbers. Okay? So you first got to figure out what the most important functional group is. That's the only one we got right now, is this double bond. And we're going to number from this end of the chain because that's the lowest number system. If we number from this end, we say 3. We don't want to do that. 1, 2, 3. We want to number from this end because that gives us the lowest number to the only functional group in this case, which is the most important functional group because it's the only one.
Are you numbering the carbons or the bonds?
Carbons. Numbering the carbons.
So you're going to go 4.
Hmm?
So it's going to be 1, 2, 3, 4.
Mm-hmm. Well, you actually never number 4. Well, not yet anyway. There are times when you do, but not yet. Okay, because 4 would mean you'd be flipping. It's just going the other way. You can number from this side if it gives you the lowest numbers. Doesn't matter which end you start from, as long as your numbering system gives you the lowest numbers to the most important functional group.
What is a functional group again?
Okay, we haven't gotten to the definition yet. Okay, so a functional group is basically anything you change about the chain that's something other than a single bond between carbons. Okay, so it can be a functional group like double or triple bonds between carbons. It can also be other things we add on the outside, which are also sometimes called substituent groups.
So what did you just say?
Substituent groups, meaning we're substituting for the hydrogens. That's all it means. Mostly we're going to use the term functional group in here. Okay?
Can you repeat what that is?
A substituent group.
Sure.
Okay. Most functional groups will be substituent groups. Substituent groups primarily mean it's substituting for a hydrogen in what would otherwise be an alkane. Okay? Substituting for a hydrogen in what would otherwise be an alkane. Now, let's see, where did I do the original butane? Here's our original butane. Here's another word I'm going to throw at you today. This is a saturated hydrocarbon because it's got as many hydrogens on there as we can get on there. Okay? This is saturated. This then is unsaturated because it doesn't have all the hydrogens we could put on that set of carbons. Okay, if we could get rid of this double bond and put 2 hydrogens on there, then it'd be saturated. Does that make sense? So saturated and unsaturated.
Can you point out the saturated one again?
Yeah, this is saturated because you've got, on this number of carbons, we've got all the hydrogens we can get on there. In this set of carbons, same number of carbons, we've got less than all the hydrogens we could put on that number of carbons because of the double bond. Anything primarily is double and triple bonds that unsaturate a hydrocarbon chain.
So it's unsaturated because of the double bond?
Yep, this is unsaturated. And you've probably heard of unsaturated or saturated oils. Okay? The double bond actually stores more energy into this chain. So, I don't know, it depends on who you're talking to and which nutritionist is writing it. Unsaturated is supposed to be healthier for you than saturated because you get more energy out of it. Yep.
So anything that, if the carbons have a single bond, it's always going to be saturated.
Mm-hmm. And if it's nothing but single bonds, it's also called an alkane. That's assuming you don't have other things on there besides the carbons.
So
Okay?
saturated is what?
You have all the hydrogens you can possibly put on that number of carbon atoms.
Would that also mean that all alkanes are saturated and all alkenes are unsaturated?
Yeah, I would say that's probably true. All alkanes are saturated. All alkenes are unsaturated. Yeah. Now that's a simplistic definition. There's always exceptions. You know there's always exceptions, right? Okay. Let's see here. Let's see if we can find you some practice work to do.